So to be honest with you guys, I didn't think I would keep doing mayterials, but you know, it's pretty fun and it's May 4th, so why not do the second prompt of mayterials, which is going to be summer. So for this one, I'm going to be making a beach ball, again with vector displacement. I'm going to show you how to inflate it, how to do all the node shit. Either way, it's going to be an exciting little tutorial, so get hyped, you know, get your favorite robe. I don't know, let's just get started. So here's what we're going to be making. Here's the blend. Again, it's going to be available on Patreon. I say that because Patreon is the way my business runs. But either way, here's what we're going to be making. We're going to be making a beach ball that is, again, entirely comprised of a cube. If you didn't see the first tutorial, watch it, because this is just going to be more confusing than the first one. So we're making it out of a cube. I made this morph slider. Additionally, we have an inflation slider, which is kind of a new thing. With the corrugated metal before, we didn't really have any change, really, of its like shape. I mean, we had a bit. But for this one, we're going to be talking about changing forms and actually moving the texture with it. So you can see this red, blue, yellow, all sticking to it. And then finally, I always add in a rotation slider. So if this is something you're interested in making, well, you're already like a minute and a half into this. So let's begin. I'm going to be starting with a fresh blend file, Blender version 2.92, I think. You can use Blender 3 even, I guess it's out. I don't really care. Just make sure you're using cycles. Speaking of which, let's set up our scene. I know it's a bit laborious, but whatever. So again, cycles, I'm going to go through this quickly. Cycles, because this is the only way we can see vector displacement or displacement in general. We're going to set this to experimental. Why? Because we're going to be adding in a lot of geometry for our displacement, meaning we're going to add in a subdivision surface modifier. And when you enable experimental, we get this adaptive subdivision setting that we otherwise do not get. This is going to let Blender subdivide however much is necessary. I don't need to put in a number. Okay, it's actually more optimized than a high level of divisions. Anyways, I'm spending too long on this. For the material, settings, you already know the drill. Displacement, make it displacement only, which the name doesn't really make much sense. It still has normal mapping, but this is the one that doesn't have glitchy lighting. And then finally, just for the environment, since I don't want this kind of like unevenly lit light bullshit. No, thank you. We're going to be using an H2I, and somebody commented, hopefully you're watching, somebody commented that I always use this Leiden Hall Market. And you're goddamn right, of course I do. I just like the lighting of it. It's like more high contrast than the others, because it's like indoor and outdoor in a sense. Either way. To make it invisible, film, transparent, and otherwise we are set to go. So let's make a beach ball. Starting off with shading workspace, we need to make a material. What are we going to call it? Of course, we're going to call it Patreon, because that's where you get the blend for this. In cycles, we can now prep our material. So again, BSDF surface information, right? This is the second step. The first step is changing our cube into a sphere. In other words, vector displacement. So we're going to take care of that first, and then we'll come back to the BSDF, adding in colors, etc. By the way, before we start, my tea has steeped sufficiently long, and this is a summer relaxing tutorial. So we are going to be making tea on the fly. Chamomile vanilla. Would recommend it. I'm speaking like a fucking lunatic. Okay, so BSDF is second. Let's start with the vector displacement. Remember from the last tutorial, again, please watch it, we want to start off with our coordinate system before doing anything. Ideally, again, we'd want to use object coordinates because it's centered on the origin and it gives the three-dimensional vector position of every point on the surface. Sounds pretty good. However, again, it does not move with the transformation, whereas generated does, which is especially useful for this tutorial. So what we did is we took our generated coordinates and we just did a bit of math to transform them into object coordinates. Again, we need to center the origin from the bottom left to the center. We do this by correcting by the vector, I guess it's minus 0.5 on x, y, and z. So you can see now this thing is centered. And then finally, we just need to apply a scaling to make sure that on the x, y, and z goes from -1 to 0 to 1 instead of -0.5 to 0 to 0.5. Either way, scaled by 2. Okay, what does this do? It gives us object coordinates that, again, are based off of generated coordinates that look identical to these. So here's object coordinates, and here's our generated ones. They look the same. Whatever. By the way, I always mention this. If you are wondering what these node previews are, it's an add-on. It's called Node Preview. There's a link in the description. Check it out if you care. I just use it for my explanations. So here we have our modified texture coordinate system. Let's also save this. I'm going to give this a name that I can find later. We have our texture coordinate system. let's start doing our vector displacement. Again, vector displacement is a transformation. It is not the final position of the vertices. So think of it as instructions on how to get from one place to another, but it doesn't bake in the final position. What does this mean? It means, just for the ease of use and because it makes sense, we're going to do a vector math subtract, and we are going to subtract this from itself, in other words 0, and apply this to displacement. So again, nothing's happening in displacement. We're displacing by 0, we're subtracting by itself. But the nice thing about this is we can bake all our vector displacement instructions into this chain right here and then subtract away the original coordinates. Again, it's a transformation. Okay, I've said it enough. So again, this whole chain we are not going to be dealing with. We just care about what happens here. Okay, so first thing we need to do, turn the cube into a sphere. How do we do that? Good question. It's actually much easier than you think. So you might think, okay, you have a sphere, you have these polar spherical coordinates. How do you transform? Don't think about it that way. What is a sphere? It is a set of points that are equidistant from, say, at the origin. Okay, so if we can make all these vectors of the cube, instead of like having corners and all this, we make them equidistant, it's now a sphere. Because right now, some corners are further away than the top of the face. So all we need to do is we put in a node again in this chain over here that again we're going to subtract away from the original coordinate system. So this is the second step in our vector displacement. For this, we are just going to set it to normalize. What does normalize do? It takes a vector and turns it into a unit vector. Same direction, but now it has a length of 1. And that's the thing for all vectors. So that's going to make it a sphere because now these are all equidistant. They're normalized. By the way, at this point, if you wanted to change the size of your sphere, you just do scale, and they're going to all scale uniformly because, again, they all have the same unit length to begin with. Cool. So we have a sphere. Let's see what this looks like. It looks like a sphere, somewhat indistinguishable from a geometric one. But again, the bounding box is a cube. We made this with vector displacement. Next, what I'm going to do actually is I'm going to make the colors of the beach ball, so BSDF information, and then we're going to start going back and forth between vector displacement and BSDF. So what does a beach ball look like? It has like a red stripe, a yellow stripe, a blue stripe. Some of them are American themes. You have 3 colors usually, and they go around the thing of the sphere. It's almost like we're looking at the angle as we're going around. Speaking of which, let's get some angle information so we can do that. So, like I talked about in the last tutorial, when you do vector displacement, always use the last step of vector displacement for your surface. Okay, so I'm not going to use any texture coordinates here. I'm going to use these modified ones with the vector displacement. So what I'm going to do is I'm going to separate by XYZ. Again, what I'm doing here is I'm using the last step, and what we're actually doing here is trying to find the angle of the sphere. So if we separate by XYZ, you can see we are looking at the x-axis, left to right, and here's what it looks like on the sphere. Y-axis, and hopefully z-axis should work as well. By the way, if we were to take this and scale it, and I'll try to speed up in a bit, I just want to get the fundamentals in here. If we were to scale this, you can see now we have a magnitude of our transformation, and the texture in some sense moves with it. And this is because we're using the last step of that. Either way, we need to use this X, Y, and Z information to get an angle. Here's the trick everybody uses. I've talked about it before, but it's a little secret. You take a math node, you set it to arctan2. This is arctangent with division baked in. If you've ever taken a trigonometry class, you know that tangent is opposite over adjacent, so arctangent kind of gives you the angle. Don't worry about it. Point is, you plug in Y, you plug in X. If you picked arctan1, you're going to have to divide y divided by x and then plug it in. Arctan2 is a single function. And what it does, as you can see in this node preview, is it actually gives us the angle as we go around here. Now, not perfectly, like it starts at 0 and then progresses to some mystery number, which I'm going to show you what it is. So if we set this to greater than, you can see we are sweeping around this, which is a good way to make our colors of the beach ball. We're sweeping around it till we get to it's pi, okay? But more interestingly, if we go the other way, it also does it to negative pi. So what this angle is, it's 0 to pi, 0 to negative pi. We want it to be 0 to 1 all the way around. So simple remapping, map range. If you ever think of the word remapping, map range. It's a trick. The cars outside are going bonkers. Either way, we're going to take the input interval of minus pi to pi, this thing that we don't want, and we're going to transform it to 0 to 1. Okay, so now we have a nice 0 going around the angle all the way to 1. And this moves with the transformation again, if we were to scale it, which I got rid of. Anyways, now we can make the colors of this thing. So what I'm thinking is we could do this mathematically, or we could do it the easy way. That's easily modifiable with color ramp. So with color ramp, I'm just going to add in a bunch of these. We might need to add in 1 or 2 more, I don't know. Just add in a bunch of these with the plus thing. We're then going to distribute them evenly from the left or the right or whatever. So now you can see we have a bunch of these, and we're going to basically make it alternating. So we're going to have one of these be white, one of them be red, one of them be white, one of them be blue, until we get to all the colors that we need. So first of all, I'm going to make this white. Control-C while hovering over it. Control-V, V, V. This is a trick that works. Cool. And now let's do the alternating thing. So again, this is surface information. So we're going to start with white. The second one is going to be red. Next one's going to be white. Next one's going to be yellow. I don't know. Look at whatever beach ball you're trying to make and just make those colors. And you can see it's kind of working. They're kind of distributed in a weird way, but we'll fix it. So we have this, 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 and then white. And then we don't need this one. So let's subtract it. And in fact, I don't even think we need this one. So I'm just getting rid of the handles we don't need. And you can see now they're kind of, the blue's taking up a lot of it. Just take this, distribute it from left again, and that should... other than the gradient, of course, I think that should be evenly distributed, okay? So what's the issue now? Why does it look so weird? It's because it's doing a linear gradient. It's trying to blend these colors together. We don't want that. Just set it to constant, and that's going to make harsh cutoffs, which looks good. We've divided it into 6 sections dictated by this. And again, nice thing about this, procedural, you could change the colors. So there's our colors. If you look at a beach ball, you're also going to notice there's a circle up here and on the bottom where it's white. It kind of excludes this rule. So I'm going to include that as well. And then we can put this on the BSDF. So again, we're using the last step of our vector displacement. It's this one. We've used it to calculate this color ramp. I'm also going to use it to calculate the circles. So for the circles, I just want to get the top and bottom circle that are centered on the top and bottom of this thing. What's an easy way to do that? Well, since these are vectors, you could take the length of them, but it's 3-dimensional, it's spheres. So what I'm going to do is a bit of a manipulation. I'm going to take this, I'm going to set it to multiply and feed this in here. So again, we're taking our transformation, feeding it in here. I'm going to set this to 1, 1, 1 so nothing changes. And the key insight here is I'm going to suppress the z-axis. So now you can see it's gotten rid of the blue channel. So before, after, check out node preview. It suppresses the z channel, which means now when we look at the length and try to get a distance function for the sphere, it's going to negate the 3rd dimension. Either way, we take this, we take this without connecting it to anything. I'm going to feed this in, set it to length, and what's it going to give us? This will be a good visual demonstration. It's going to give us a dot on the top of the sphere and also on the bottom. Now, if we were to keep this at 1, you can see it kind of goes away. This is because it's taking a 3-dimensional distance thing. This is why we're doing it 2-dimensionally, because it works on the top and the bottom, and it's easy. So you almost want to think about this as we're projecting this on the top view. So it's almost a 2-dimensional circle, then we're taking it, okay? We have a circular gradient. This is the exact kind of thing that we'd need to make circles. So instead of having it go from 0 to 1, 0 being the center where the vectors are length 0 away 2-dimensionally, instead of that, I'm just going to filter this through a greater than, so we just kind of have a harsh cutoff. And instead of that, we can make it a less than, so the center is white, everything else is black. Okay? What I'm going to do is I'm going to take this. We want the color ramp to be the way it is, except for in the circle, it's going to be white. So easy way to do this. Color ramp, factor. This factor map is going to tell us where do we want something else to be. So in this white circle, and let's see what this looks like. We can pick whatever we want there to be in the center. So again, we're taking this thing, we're puncturing a hole through it, dictated by this factor map, and then we pick the foreground. In this case, we want it to be white. So you can see it's a break in this, and not only that, it's procedural. We can change the size of it. I think I wanted 0.15 when I did this originally, but we can always change it later. Okay, so it's looking, kind of correct. It's also kind of looking flat and 2-dimensional and shitty. Is this because we did a bad job? No, it's because we're not using BSDF information. So far, a lot of vector displacement. We've done a bit of calculation with the color ramps. Let's actually have it pay off. So with the BSDF, I'm going to use this on the surface. I'm going to plug this into the base color. So if we unhide, it's in the base color. So now we have this thing that's actually shaded. I'm just going to put it on the ground, and I know technically this isn't very November material to use another object, but whatever. This is just scenery. I'm excluding it. So now it's going to reflect some white light, and beach balls are actually fairly shiny. Not like a mirror 0.2, but like, a bit more than that. So 0.3, very reflective. It's already looking pretty good. Let's make it look a lot more realistic. So first of all, we need to rotate this so it's not like pointing directly up. That's weird. But also I want to add in some distortion. This thing is essentially a balloon. Yes, if you inflate it well, it's going to be very spherical, but assuming that you didn't, it's going to have some ripples and stuff like that. So we want to distort this with some noise and some randomness. So we already know how to do that, so let's just do it. So again, last step in our vector displacement. Again, this subtraction is kind of the final thing we feed it into. The last step was actually this normalize that we used to calculate all this color ramp stuff, but last vector displacement was the normalize. So what I want to do with this is first, let's distort it, then let's rotate it. So again, whenever we want to add in a source of randomness, noise texture is a great way to do that, although you don't want to plug it in. Noise texture is basically a node that has randomness. It's noise. To have both of these mixed together, of course, we're going to use a mix RGB, so we want our vector displacement with contribution from our randomness. So we just plug both of these in. You can see it's doing a thing. And visually, we have our texture coordinates, our vector displacement up till this point, the normalization, whatever. We're distorting it, and you can see this is what it looks like, the distortion. Again, we always have this issue where it's kind of drifting off to the corner almost, you can tell. The origin's moving to the corner, and in 3D space, it's going to move up to the corner of this bounding box because we're, in some sense, adding the vector 0.5, 0.5, 0.5. The fix for this, I'm not going to talk about it too much here, but the fix for this is you set it to linear light. This keeps it centered during the transformation. What's going on here is noise is a 0 to 1 random value on the surface for each point. So on average, we're adding 0.5, 0.5, 0.5, which moves everything on average to the top right corner. Either way, now you can see we can kind of control the strength of this. So we can have a nice little ripply thing, which adds a lot of realism. But I want to control the quality or the type of randomness. So first of all, I don't want this to be so ripply, like a lot less dense. So I'm going to bring down the scale so it's more like low frequency information. And now let's try changing this. So again, like we could change stuff like the detail we wouldn't want to. You can see this makes it more harsh. This is the kind of things we want to consider. So I'm going to have low detail, something like 1.5 or something. I don't even, maybe it's an integer thing. Either way, scale of 2, detail of 1, and then a very low distortion value, which is essentially the mix value. So here's before, here's after. It's subtle, but it helps. And I'm going to keep it at 0.045. Okay? Cool. And since this is a noise thing and it's procedural, by the way, you can use this as a seed value to get different types of balls, or you can even have this animate a bit, as you can see. But I'm just going to keep it at 3D. Okay, cool. Next step in our vector displacement, I just want to rotate this. Easy way to do that. Again, next step in our vector displacement, we add it to this chain that eventually is going to be subtracted. I'm going to set this to Euler. Vector rotate's going to rotate our thing. The reason I do Euler is it boils down to X, Y, Z, centered in the middle. It's easy. So Z rotation, X rotation, Y rotation. You get the deal. So I'm just positioning it in a more kind of visually interesting, composition-y kind of way. Okay? So far, what have we done? We took the cube, we normalized it. That makes it a sphere. We've added distortion. We did all this calculation for the colors. We rotated it. And it looks like a beach ball. So I think we're done. But I said I'd also include the inflation animation, so let's talk about that too. But as for the final thing, I think it's done. Like you could add some normal mapping, some dust, but I think it looks pretty good. So how do we do the inflation? Well, so this is the kind of thing you'd want to do with a cloth simulation, right? If it was up to you, you'd use the pressure settings and all this. And technically, you could do that on the cube and it will work as a bounding box, kind of. It's weird. But since we really don't have access to this information, it's all procedural, we're going to need to fake it. So here's the simple idea. You could do it much more complicated, but I'm just going to keep it simple. I'm going to have one state where the beach ball is as it is. It's done. I'm going to have another state where it's flattened and like, deflated, uninflated, deflated. And we're just going to transition between one and the other. It's not technically a good way to do it, but it visually looks good. So we have the first state. basically everything leading up to this point is the first state. Now let's make the second state. So what I'm going to do is it's basically the same thing that we've been doing so far. I'm just going to blend the two together. But for now, let's just treat it like we're making it deflated. I'm going to take this, I'm going to multiply it. So it's going to have all the rotation and everything baked in. I'm going to multiply it by 1, 1, 1, so nothing changes. But on the z-axis, I want to flatten it. So I'm just shrinking it on the z-axis. The flatter, the better, like pizza. So we flattened it. I also want to make it a bit smaller this way. And this is actually a key insight here. You can see the texture is actually stretching with it during this transformation. Again, if we were using object coordinates for this, so let me just do a quick demonstration. If we were to use object coordinates for this, you can see there's some drift. So that's why it matters. I'm glad I could show you that. So again, we want to position it where it should be. So we flattened it. Now let's do an addition, which again, you can think of as a translation. So I'm going to add the vector negative something on the z to move it down on the z-axis. So again, multiplication is stretching. Addition is just moving or transforming, whatever you want to call it. By the way, it should be the same thing on x and y. Okay, so we have this and this. I also want to add in a bit of like, you know how the thing folds in on itself. I'm just going to add in a bit of distortion. We could do it the same way we did before, but it's actually going to intersect on itself and it's going to look weird. So I'm going to add in a bit of randomness like we did, but this time only on the z-axis. So let me show you how to do that. We could do this with mix RGB. I'm going to do it kind of the lazy way. I'm going to add in a vector 0, 0, 0, so nothing changes. I'm going to put in a custom vector that we can control the x, y, z components of, and we only want to change, whoops, that is too much. We only want to change the z, but by some noise value. So for example, if I was to take this, plug it in here, now you can see it's distorting on the z-axis. Now, I didn't do this for the original, but I'm considering doing it now. I'm going to add in another noise texture. So before, I used the same noise texture for both because it calculates faster, so it's worth it. But I want to experiment with if I can make a custom noise, just so I can get a nice rippling. So what I want is I want this to be a lower scale, less stuff going on, maybe more detail, so it's a bit sharper. And also, we want it to be way less intense. So before we even have it reach the z component, let's multiply it, which is the strength. Again, when it's 0, nothing. When it's 1, a lot. Let's multiply it by something kind of small, until I feel like it looks correct. That kind of looks pretty good. And we can control the quality of our noise. I don't think that looks too good. Maybe some distortion, but not too much, would make it look interesting. I'm going to lower the scale, add some distortion, playing around with numbers until it looks right. So you can see there's some self-intersection here. You want to avoid that if possible. And if you can't avoid it, you just change this W slider until you get something that looks good. But I think that looks pretty okay. That kind of looks deflated in theory. So again, let's go to the side view. You can see that this on average moved everything up. We could have fixed that with a linear light, but I'm just going to do this manually. So that addition we did before, let's make it go a bit lower. Okay. So how do we want to think about this? Well, everything up until the vector rotate node was just our beach ball. So you can see if we plug it in, it's our beach ball. Then everything after is the other state of it. It's the flattened state. So what I'm going to do is I'm going to take all this and select it all. Shift P makes a frame, so we can just think about it as our second state. And again, the idea here is we want to mix state 1 and state 2 in an interactive way. Well, easiest way to do this is like you'd think, mix RGB. We mix both of them. So I'm going to mix the first one with the second one. And now you can see we have a slider that goes from deflated to inflated. Yay! And you can even add in a bit of bouncing and stuff like this, but whatever. So all of this is procedural. It's made in a chain so that if I was to like rotate this, so the beach ball is now rotated this way, it will deflate facing the same direction. It all makes sense. So let's think about it. We've done the BSDF, we've done the surface, we have the initial state, we have the final state. It looks pretty good. Like that's kind of what it would look like if it inflated. Again, what you could consider doing, and here's how you do it, is you make it like hop up and down a bit. You do that by moving this up and down on the z-axis, but whatever. In essence, though, that's kind of the thing. You just make it a nice little node group at this point. So you have control over this, maybe control over the rotation, etc. But I think for the beach ball, that is the essence of it. Okay, we've done it. We've made it to the end. Whoa. Have I been on the bottom of the screen this whole time? We made it to the end of the second day of mayterials. What is this on the right? Is it a list of the number of times I flip-flop about whether I'm going to do the full month of May? Just so you know, I'm definitely not going to do the full month of May, but I might do a couple more days of this because, I don't know, I like doing vector displacement. No, it's a list of patrons. What do the patrons get? Well, they get the blend file. I ingrained that into you sufficiently, I think, at this point. I said it like 1,000 times. They get blend files for anything I've ever uploaded on Patreon. Link in the description if you're interested. Additionally, exclusive tutorials that I'm going to do a couple times a month in general. They're not available on CG Matter default cubes. So for example, maybe Mayterial Day 3, I'll upload there. I don't know. But you get those, Discord access, early access to tutorials. This one is going to be available early, I can confirm that. And a whole bunch of other stuff. So Patreon exists. It's worth your while. It's very cheap for what it is. It's monthly. So check it out if you care. Also Node Preview. It's a thing. And yeah, that's my time. See ya.